Hi! So in the last video, we went through what is a static game, what is a strictly dominant strategy, strictly dominated. So we talked about the idea of dominance, and we used a process of eliminating strictly dominated strategies using IESDS. But we also seen when it fails, and this gives us another notion that we need, and that is known as the Nash equilibrium. So we seen when the IESDS fail in the battle of the sexes, and so this doesn't tell us what strategy should be taken. And so we now find that there will be two possible outcomes. Either you choose fight or ballet in battle of the sex game, and in each outcome every player is actually already in their best position, because if you are here, Bob will not want to choose ballet since it will give you 0. Likewise, Alice will not choose ballet because you go from 1 to 0, and the exact same for the ballet case. So there's no incentive for you to deviate from this outcome. And so let's first give the notion of a best response function. And for this case, we see that a best response function is basically you choosing. So if let's say Bob chooses fight, what's your best response? Fight or ballet? That's fight. So you choose the action that gives you the highest payoff compared to the other actions. So you can see a bit how it's a little similar to the strictly dominant notion. But in this case, you are not choosing. Let's say Bob chooses, you fix maybe Bob. Then you see for fight and ballet, does fight always give you better than ballet? So that's the dominant notion. But for best response, it means that if you fixed a specific action already, then Alice choosing fight or ballet, then you just highlight the better response. And so for the battle of the sex game, we see this the outcome. The best response for Bob to Alice fight is fight. And so a Nash equilibrium now is just a strategy profile such that everyone's strategy is a best response strategy, and so it means that you maximize the payoff for that action. And in words, it says that for every player and every strategy chosen is at least as good according to the player's profile, the player's preferences. So in other words, the players has no incentive to deviate. So it's actually a mutual best response. So this mutual best response is important. It means that if let's say my best response is some graph like this, and the opponent's best response is some graph, then the mutual best response is of course the intersection. So it's actually the intersections of everyone's best response function. So this definition implies neither that a strategic game must have a Nash equilibrium, nor it must have only one. It is possible for some games to have single Nash equilibrium, like the Prisoner's Dilemma, while in the Battle of the Sexes you have multiple Nash equilibrium. So, and there are some games without a Nash equilibrium even. So what's important to note is that a Nash equilibrium is just a state where so both of you guys choose an action, and that action is the best response to both of each other's action. So there's no incentive to deviate from one another. So now we'll take a look at how to find the Nash equilibrium, and it is quite simple actually. The process is very straightforward. So for each strategy, let's say player 1 chooses T, then you just underline the players 2's best response. So in this case, it's 403, so you underline L, which is 4. For M, then it's 043, so you underline this. And for B is 556, so you underline the last one. So it's this, and this. Then you do so for player 2. When player 2 chooses L, your best response is M. When player 2 chooses C, your best response is T. And when player 2 chooses R, your best response is again B. And now, you see that there is one state where it underlines 2 times. So that is called the Nash equilibrium. And then because this is the only state that has 2, this is the unique Nash equilibrium. Now, like I said, that the Nash equilibrium, the definition, the best response function, it looks similar to the dominance notion. And why? There's a link between them, and this proposition states it. And it is that every Nash equilibrium will survive the IESDS, meaning a Nash equilibrium cannot be a strictly dominated strategy. And the proof is very simple. You're always choosing your best response already, so it cannot be strictly dominated ma. So in that case, it will always survive a round of IESDS, and this keeps surviving. So it will always survive the entire process. And if an IESDS leads to a unique outcome, then it is a Nash equilibrium. The formal proof is over here. But I like you to think about it intuitively. If you eliminate all the strictly dominated strategy, then this last strategy that you choose dominates everyone else, then there will be no incentive for you to deviate, and that will mean it is a Nash equilibrium. And in formal way of writing, you can see it over here. But the problem is now, even though that's the case, even if you know that there is a Nash equilibrium, there may not be a unique IESDS. So this example shows it. So in this case, you see that B is weakly dominated by T, and R is weakly dominated by L. But we still have a unique NE. So the NE may consist of weakly dominated strategies. So the IESDS gives us nothing because it's all weakly dominated. But there is still a unique NE, and this is due to the weakly dominated strategies. So that's all for this video. So I hope now you understood more about the Nash equilibrium, as this will be one of the most important notions throughout game theory. So that's it, and I'll catch you in the next one. Bye!